So in this video, we're going to talk really quickly about how to tell if two events in probability are independent, which means the outcome of one doesn't affect the outcome of another. Something like rolling a die and then rolling a die again. The second roll isn't affected by the first roll. So we've already talked about this rule here. You can tell two events are independent if their combined probability is the same as the probability of one times the probability of another. So that's one test you can do to see if two events are independent. There's another test that I'm going to introduce today. To introduce it, imagine you're going to flip a coin 2 times. What is the probability that the second flip is tails? And then also think about what's the probability that the second flip is tails given the first flip is tails. Are these going to be different at all? They really won't be. The probability that any flip of a coin is tails is going to be 1/2 or 50%. And it doesn't matter what the first flip was. That's not like just because I flipped tails once doesn't mean I'll flip tails again. So this right here basically tells me that those are independent. The first flip did not impact the second flip's probability. These two were the same. And this is basically the rule that we're going to talk about. Two events are independent if the probability of that event given that B happened is just the same as the probability of the event in general. Like the probability of flipping a second tails given you already flipped a tails should be the same as just the probability of flipping tails. Like this given really is kind of irrelevant. That tells you that the two events are independent. And we already talked about that rule. Okay, so for example, imagine the probability of A is 0.82 and the probability of A given that B happened is 0.82. Are they independent? Yes, literally because these are equal. The fact that B happened didn't change A's probability, and so that makes them independent. However, in this case, probability of X is 0.82. The probability of X given that Y happened is 0.41. So somehow the fact that Y has already happened affected the probability somehow. And so X and Y are dependent. They are not independent. On this one, rolling a 4 on a single 6-sided die, and then rolling a 1 on a second roll of the die. Again, come on in. Let's see, I'll be done in 1 sec. Again, these are independent because the second roll is not going to be affected at all by the first roll. Let me see here. And if you wanted to prove this, you could do this. So like the probability of rolling a 4. Probability of rolling a 4 is 1/6. So 1 chance out of 6. The probability of rolling a 4, oh no, sorry, we're doing this wrong. Rolling a 1. Rolling a 1 is still 1/6. And then the probability of rolling a 1 given that you already rolled a 4 is still just 1/6. The first roll doesn't matter. So again, since these are equal, that proves that they're independent. Last example here. Let 60% of students be female in this particular class, and then 50% have long hair. 45% of the students are female and have long hair. So of the female students, 75% have long hair, so there's a lot going on here. Are the events F and L independent? So being a female and having long hair, are those independent? And so I have a lot of stuff here, and there's a few different ways I could do it. I could use this first rule, which is multiply together probability of being female times probability of having long hair and see if it equals the both. So does the probability of female times probability of long hair equal the probability of female and long hair, which they gave me all of that. Female was 0.6, long hair was 0.5, and that is 0.3 if we multiply those. And then it said 45% of the students are female and have long hair, so that's the both, so 0.45. Since these are not equal, that tells me they are not independent. I didn't actually end up needing this, but if I wanted to, I could. Of the female students, 75 have long hair. That's basically saying, what's the probability of having long hair given you're a female? That was 0.75. And basically, since this didn't match the probability of just having long hair in general, that also tells you that they are not independent, because these two should be the same. So either of those ways you can tell that those are not independent, and then they're dependent. All right. And we're going to